Just gonna go live. I'll let you know.
Yeah, so we are live.
We're live. Hello, everyone. We have our next talk, which is an application of Python and density functional theory by Professor Bappanaya and his team. Yes, you may please start. Thank you.
Hello everyone. Good morning. Namaskaram. Here is C. Bapanaya, lecturer in physics from SVA Government Degree College, Srikalahasti, Andhra Pradesh. So today I am going to talk about application of Python in density functional theory with a case study of cathode material, which is lithium, that is Li2RuO3, lithium ruthenium oxide. So my talk consists of introduction, computational details, and then programming codes, which I will be discussing thoroughly, and then a few computational results. So a brief introduction. As we know, Python has been used in a wide variety of theoretical scientific research activities because it offers versatile functionality and powerful integration. And for the density functional theory, which is a popular scientific computational technique to study various properties of materials, it is widely used in physics, chemistry, and material science. And such DFT codes such as grid-based projector augmented wave, in short GPA, or VASP, Vienna Ab initio simulation package, and ASC, atomic simulation environment. Such codes are all written in Python, and these codes are very popular in among DFT codes. And further advantage of these codes is these codes can be modified to suit our needs. And here we have chosen the material Li2RuO3 because it was identified as a potential cathode material which promises high capacitance, of course, charge storage capacity, and it is under very active study. And here we are going to present DFT investigation of the crystal structure of Li2RuO3, the band structure, and density of states profiles of Li2RuO3. So the computational details are the crystal structure of this material was designed in atomic simulation environment. And we have used GPA code to solve Cohen-Sham equations. Actually, these equations are the basic equations. Of course, single electron equations, Schrodinger wave equations, and GPA actually works as calculator, DFT calculator. And the design structure was relaxed for actually optimization for minimum energy using the BFGS algorithm. And this is one of the local minimization technique available under DFT. And we have used optimized real grid spacing as 0.2 angstroms. It is the beauty of this GPA code, as it uses real space to expand the wave functions or to present the wave functions. And we used 64K points in irreducible part of the Brillouin zone, or we can say that Brillouin zone was sampled so that we have 64K points in the Brillouin zone, and a cutoff energy of 400 electron volts was used as a part of the calculations. And we have set the convergence criteria so that maximum of 0.05 electron volts per angstrom units force is allowed on each atom. And there is one more exchange correlation functional. We have used PBE, generalized gradient approximation, which is best suited for DFT calculations. And my actual program code goes like this. The program code consists of first importing all the modules necessary for the computation. So my first module to import is Crystal, and it comes from the ASC package, and space group sub package. So from ASC.space group, import crystal module, and then we have to import calculator and the subsequent modules such as GPA, PW. PW stands for plane wave, and Fermi-Dirac stands for Fermi-Dirac smearing. And as a part of relaxation of the unit cell, we have used extra relaxation parameter from unit cell filter module. It comes from the constraints part of the ASC, atomic simulation environment. And then the local optimization technique, BFGS was imported from ASC.optimize, and then read on write, as we know, to read the files and write the outputs, we have to import them. And then for visualization purpose, we have imported view from ASC.visualize. And then one needs to define the unit cell of the crystal, and that was defined from the by using the crystal module. So my name of the unit cell goes as Li2RuO3, and the module crystal, it takes the arguments. First argument is symbols. Here we mention all the atoms, of course the symbols of the atoms which we use as basis of the unit cell. Here 1 Ru atom and 3 lithium atoms and 4 oxygen atoms forms the basis of this particular unit cell. So the basis is equals to, we have to use the position coordinates as per the sequence of the symbols. So first we have to use the position coordinates of ruthenium atom, and then lithium 1, lithium 2, lithium 3, lithium S, and then oxygen 1, 2, 3, 4. This forms the basis of the unit cell. And of course, the position coordinates may be acquired from an experimental data, or we can choose an approximate position coordinates, because anyway we will relax the unit cell so that the position coordinates will change subsequently. And the space group which we want to optimize is the international space group number is 11, and this goes for P21 structure. And the cell parameters are alpha, A, B, C, and lattice constants, and alpha, beta, gamma, or angles. So these are the approximate unit cell parameters, which actually we have acquired from neutron Rietveld analysis by Muir et al. And then PBC, periodic boundary conditions, I have enabled as true, and primitive cell false, because unless you are dealing with actually very minimum volume unit cell, otherwise we have to make it false. Next, a calculator has to be defined. Here
you have 5 more minutes for
okay, sir.
including Q&A.
We have taken GPA calculator, and the arguments are mode. We have chosen plane wave mode, where cutoff energy is 400 electron volts, and exchange correlation function XC as PBE, and real space grid size 0.2 angstroms, and K points 444. This amounts to 64 K points in Brillouin zone. And the random, yes, actually it is the random guess. If more empty bands are required, that is enabled, that is true. And occupations from Fermi-Dirac, which has a width of 0.01 electron volts, and the output of the calculations, all data will be saved in a text file. And then this calculator has to be defined, attached to the crystal we have defined in ASC, that is Li2RuO3 calculator, within brackets calc, that has to be attached. And then in the part of structure optimization, we have to use unit cell filter module, where the argument comes as the structure itself, and the output is stored in UCF, and this goes into the BFGS optimization algorithm, where you can take maximum displacement of each atom as 0.4 4 angstroms, and all the intermediate structures, stabilizer structures, will be stored in a trajectory file, and the summary of the optimized steps or energies will be stored in a log file, and this optimization will run for up to F maximum 0.05 electron volts per angstrom on each atom, and the output will be, or calculation results will be stored. You can store it in several different files, but a calculator specific file is more advantageous. So the GPW extension file will be more advantageous, and we can view the crystal by simple command view. And optimized crystal structure information can be stored in different formats: CAF, XYZ, or cube file, whatever it may be. And then band structure can be actually plotted, calculated and plotted by using the simple Python commands. Again, the calculator has to be refreshed, restarted. The optimized structure goes into the argument, and total number of bands considered is 16, and density has to be fixed. And K points, actually this is the high symmetric path which we have to define. Since it is a monoclinic structure, these points are the highly symmetric points, and we have considered bands to converse. And calc.band structure actually calculates the band structure, and we can plot and save it as a PNG file. Here Emax equals to 5 means above the Fermi level or below the Fermi level, we are using we are calculating the band structure up to 5 electron volts. So we can use save the file by this command also. And actually density of states can be calculated from
You're running out of time, so I suggest you
okay, sir. Final computational results. So we have got the stabilized structure Li2RuO3, where it consists of 24 atoms, and actually it is a honeycomb structure. Here the lithium atoms are intercalated, which are available for extraction, and the band structure looks like this, and DOS profile like this. And this is the projected density of states, where we can actually calculate lithium s orbital and oxygen p orbital and ruthenium 4d orbital density of states, and this looks like this, and our results are exactly in agreement with the those results available in the literature. And so we have studied density functional theory calculations in Python based GPA code, and the crystal structure was optimized, and the calculated electronic properties are in good agreement with the data available in the literature. Thank you very much. Thank you for listening.
Thank you for a quick demonstration of what you can do with the many density functional theory tools available in Python. There are no questions currently, but we encourage the participants to ask you questions. I have a quick question.
Okay.
How long did this take to run? So once you set this up,
yes,
how long does it take to execute a typical computation that you need?
Actually, it takes around 12 to 14 hours for one program.
So wow! So the one program that you showed with all those results.
Yeah.
And how many programs did you have to run to get those kind of results?
So for one structure, actually, for initial checking up process, it takes around 2 to 3 days, because we need to optimize the H value, number of K points, and so on.
Right.
And once we got the optimized values, then it is a matter of 12 hours to 14 hours.
Okay, to get the final results.
To get the final structure only.
Okay, this is only the.
And for band structure and DOS profile, we need extra 3 to 4 hours.
Wow. Okay. So in a few days, basically, you can compute these for different kinds of materials.
Yes.
Very nice. Very, very nice. Very interesting. Thank you so much. We encourage you to please hang around in the chats, both in the this platform as well as on the other platform.
Okay.
So thank you. So we now have a few minutes break. We will start with the next talk at 12:04. I will advance it by a minute. I guess everybody needs a bit of a bathroom break. We'll stop now and we'll just start again at 12:04 sharp. Okay. So see you all soon. Thanks again.